Cybernetics Made Easy. Part 3, The Governor. Some Other Models by Robert Johansson. We began with a diagram of the governor on a steam engine. We then translated that diagram into a schematic of the process. The changes in drive speed are translated by the gear into perceptions, or the speed of the spindle, which are translated by the flyballs into needs, or a change in the sleeve, which indicates faster or slower, which are translated by a lever into a change in the steam valve position, which then is translated by the steam engine into changes in the drive speed. It may be worthwhile discussing the governor using some of the traditional cybernetic models. B.P. Lathy, in his book Signals, Systems, and Controls, presents this schematic. An input goes to a controller, which sends a control input to the plant, which produces output. Information about the output is then fed back to the controller. So his model of the governor would look something like this. A goal goes into the governor, which controls the throttle position, which then the steam engine turns into drive speed. Information about the drive speed is then fed back to the governor. It is the information process of the governor which controls the valve, which controls the steam engine. Control systems are information systems. In Norbert Wiener's 1948 book, Cybernetics, we find the following diagram of a cybernetic system. A subtractor gives information to a compensator, which sends information to an effector, which produces an output. Information about the output is then, by a feedback takeoff, sent back to the subtractor. Wiener was engaged in making automated anti-aircraft guns. Thus they would get a target input, shoot the gun. Then they would compare where the bullets were to where the enemy aircraft was. If you took the target position and subtracted the bullet's position, feedback, then you would have the difference. You could then use that to adjust the aim of the gun, the compensator, and then fire the gun again, effector. So his model of the governor would look something like this. The goal is fed into the flyballs in the form of their position, and that is connected by the lever to the steam engine, which produces the drive speed. Then there is a feedback takeoff from the drive speed via the gear, which gives information back to the flyballs. Ludwig von Bertalanffy, 1968, diagrams a cybernetic system in a similar way, but he is very clear that the internal process is an information process. Thus, the stimulus to a receptor turns into a message which is fed to the control apparatus, which produces a message to the effector, which produces a response, which is then fed back into the receptor. His model of a governor would look like this. The goal is placed in the flyballs, which controls the position of the sleeve, which is a message to the lever, which controls the position of the valve, which controls the amount of steam going into the steam engine, which turns it into drive speed. Information about the drive speed is then fed back using the gear system to produce the speed of the spindle, which is then information going to the flyballs. Now for something completely different. J. Wright Forrester developed the following model that eventually became system dynamics. On the right-hand side, you will see a big blob. That's the source. That's where the stuff comes from. And the solid line going through the valve to the inventory is the stuff going from the source to the inventory. Now, the little blue dot on the side of the inventory is the feedback takeoff, which takes information about the inventory and feeds it to the valve. Then, if you look over slightly to the left, you see the desired inventory, the goal of the system. And that is fed into the valve system. And finally, you have information about the adjustment time. And that is fed into the valve, and those three things produce an order rate, which controls the amount of material from the source going to the inventory. Forrester's model distinguishes between the information flows, the dotted lines, and the material flows, the solid lines. It makes clear the fundamental discovery of cybernetics, that information processes control material processes, and that cybernetic control systems are goal-centered. It also makes clear what the system is trying to control. It is trying to control the inventory. Since it is primarily about inventory control, applying it to a governor is a bit awkward. Thus, the boiler provides steam, which is controlled by the throttle, which is sent to the steam engine, which produces speed. The feedback takeoff is the gear, which translates the speed of the drive into spindle speed, which is information for the flyballs. Now, you also have the desired speed, and the desired speed is also information, which is fed in to the mechanism of the valve. And finally, you have the rate of flow of the steam, so that adjustment rate or flow rate is also fed into the valve, so that what happens is that you produce an order rate, the amount of steam that is controlled by the throttle and fed into the steam engine and controls the speed. Forrester's model was designed for computer modeling, so you can collapse a complicated mechanical process into a simple formula. DI, or desired inventory, minus I, which is present inventory, times the adjustment time, AT, is equal to OR, the order rate. Clearly, energy processes are a little more complicated than inventory control. Forrester's model has a time function. Thus, he could use the model to produce a graph of changes to inventory over time. The problem for Forrester's model is that it is essentially linear. It is a rates and states model. The control process is seen as controlling a linear process. As a result, hierarchical systems require the input of a variety of historical averages for the adjustment time. There are a number of problems with each of these models. The problem with the information model is that it focuses on the information process. As a result, the matter and energy processes are obscure. On the other hand, since the control process is an information process, an emphasis on the energy process will obscure the control process. Probably the most serious deficit of the mechanistic models is that they obscure the fact that the control process is a decision-making process.